All right, welcome back to the drive-thru, sponsored by the deli. Hungry? Stop by the deli and just get yourself a regular old sandwich. We don't have time for sandwiches today, okay? I say welcome back to the no one on the internet that's watching this video. If you are the person watching, I'd love for you to reach out and find me. Okay, so today we're doing the second. We're going to do 3 videos, okay? Today we're going to figure out how to find the mass of a spring. That's no different than what we've done. Now the spring is just traveling in a spiral. And then we're also going to find work, and that will be new, okay? So, voila. Okay, so it's kind of important before you start these that you just get a grasp of what's going on. This is hard to read. Here we go again. 1 plus Z is what that says, okay? So, hopefully you remember that this is half of a double helix. It's a spiral, okay? So what we've got here, let's see, it starts at cosine, so that means x will be 0, or x will be 1. So we've got something that looks like this, going 3 complete rotations-ish, because it's going to 6 pi. And then you've got a force field. Okay, or, well, I'm sorry, it's not a force field yet. You've got a density function. And describe this density function. It's more dense where? More dense at the top. Okay? So, as we travel higher and higher, the wire gets denser and denser, and we're trying to find the mass of this spring. Okay? So, what we have here is we have some information like kind of hidden. So when we do our integral, it's 0 to 2 pi, okay, this needs to be x 1 plus z. This is our density function. Sorry, 6 pi, thank you. But what are we going to call this z? We don't want a z there, we want a t there. What does z equal? Z equals t right here. Okay? So we're going to change that to a 1 plus t. Oh, you're right. That's t over radical 2. Thank you. Thank you. I even said that when I wrote that down that I was going to forget that. And I did. Okay? So 1 plus t over radical 2 times... Okay, so x equals cosine of t. So what's dx dt? Negative sine t squared t over 2, right? Because of this, again. And that is, let's see, dx dt squared, or x prime of t squared, okay? Plus what? Cosine squared t over 2 plus 1/2, right? So it's 0 to 6 pi of 1 plus t over radical 2 times, well, we got sine squared plus cosine squared is 1. So 1/2 plus 1/2. That. Sure. If that's what you want. You got it. Okay? Alright, so this isn't bad. It's the integral from 0 to 6 pi of 1 plus t over radical 2 dt. So you get t plus t squared over 2 radical 2 from 0 to 6 pi. And we'll just write the answer down as a decimal. You get 144.47 units of mass. Okay? Okay, so now we're going to try to make these more useful. So what we had was the line integral of a density function, but all of those were of t, okay, times the square root of x prime of t squared plus y prime of t squared plus z. That's what we had. I'm not writing it down because we already did it in the last video. Okay. Now we're going to talk about work done in a field. So work, well, we know that work is force times distance. Okay. So we can use that same concept and just say that it's a force field okay, times some unit tangent vector. Okay, so that's the same thing as the integral from a to b of f of x of t, y of t, so we're going to have to make those parametrics again, z of t dot r prime of t, all with respect to t. Okay? So, what we're doing, this represents a force, okay? When we dot product them with the derivatives, we are basically saying, I want to see how much force is going in the x direction. So I take the derivative of this so that I can integrate it and add them all up. It's literally like a trick. Okay? And I'm going to see how much force is in the y direction, and I'm going to see how much force is in the z direction. And again, the reason I'm doing the derivative is so that I can integrate it and add it up. It's just like finding the area under a curve. So you might ask yourself, like, how come I can't just find the force at a point by multiplying the force times the point? Well, it's the same reason you can't find area that way. To find area, you need a distance, because at a singular point, there is no area. And that's like the magic of this math. You're adding up a bunch of things that on their own don't exist. And it gives you the sum that definitely does exist and is right. Okay? So, what is r of t? Okay, r of t is a vector valued function. Think of r of t like in the last. Think of it like this. This is r of t. It defines the path in which we're traveling. Okay. Sure. That's just a screwed up part of that problem. The radical 2 has no effect. It just squashes the spring down. Okay. Makes it more springy. Okay. So let's take a look at an example, and I think you understand this better. Okay, voila, example 2 for the day. So we tried to kind of color code some stuff. This is a different type of problem. Like, notice, we have no bounds on our t right now. We don't know what to put as a bounds of our integration, so we're going to have to do that. But, again, if I could describe what's going on, which one of these functions represents the path that we are taking? The blue one. Excellent. Okay? So it's this very similar path to the last one. Is it negative? No. Yeah, it's okay. Very similar path to the last one. Now, what's this black function represent? Well, what type of function is it? It's a vector valued function. Okay, and it says find the work done by the force field. So what you would do is, if you wanted to see what this force field would do, you would plot points, right? You'd plot your vectors. And that's done for you in the book in figure 14.15, okay? So we've got some vector field here. And don't pay attention to these arrows. I'm just telling you, that's a vector field. It varies. It varies this way, okay? So as the particle moves through it, the amount of work that is done on that particle changes, and we're adding up all that work, and we'll do that right now, okay? But first of all, does anyone intuitively figure out what T is doing? How long of T do we have here? What's T doing? It's going from what to what? Okay, now look at this. This is your hint. That's right, okay? So Z equals T here. And here Z goes from 0 to 3 pi. Okay, so we want to do the integral of f dot, here's a way to think of this. That's why it's f dot dr. You're taking the derivative of r with respect to t, and then you're integrating that with respect to t, and that's the magic math right there. Okay? So, we got the integral from 0 to 3 pi of, can I write negative x over 2 there? I cannot. So what do I need to write there? Cosine t over 2, right? That was negative. Let me just scroll up a little bit. Okay, and then I'll comma negative sine t over 2, comma 1/4, right? Dotted with what's the derivative of cosine? Minus sine of t, cosine of t, and 1 dt. Okay? So what I'm doing is adding up force in the x direction, force in the y direction, force in the z direction. Got it? Alright, well this ends up really cleaning itself up. And there's a reason for that, and we'll discuss that reason. So what do you get when you dot? Somebody help me with this dot product. Sine t cosine t over 2 minus sine of t cosine t over 2 plus 1/4. Nice dt. Well, here's what I want you to understand. First of all, remember, no more vectors. What are we finding here? We're finding work, and work's a number, scalar. Okay? But what we just found out is all the work that was done in the x direction has been what? Canceled by all the work that was done in the y direction. So the only net work that we have here is in the z direction. So 0 to 3 pi of 1/4 dt. So it's t over 4 from 0 to 3 pi, and the work done is 3 pi over 4. They don't dare give us units, do they? It's in joules, right? Or foot-pounds? No? Right. I shouldn't have even gotten into it. Okay. All right, so tomorrow, this is your little introduction to differential equations, and then honestly, that might be enough. There may not need to be a third video, okay? So we just learned that that's what we were doing, but what we really said is we want to do this. Do you see how those things are equivalent? Okay? Well, now remember, we're going to treat this just so it's easy to understand, or easier to understand, I should definitely say, as a two-dimensional case. So remember from the very beginning of the chapter, these m's and n's, the functions that defined our vectors, our force fields, which is our vector fields. So we're going to dot that with dr. Well, dr is x prime of t I plus y prime of t j, and then we still need a dt here. Okay, all we're doing here is getting into a different notation, which is going to take us into a whole different math class, which is called differential equations. Okay, it's all good. It's all the same. So now we can call that a definite integral from a to b. Keep in mind that x prime of t, this is the same thing as dx dt, right? Does everybody agree with that? So here we're changing to differential notation. So you get m times dx dt plus n times dy dt, all with respect to t. And then we can write that in the differential form Any guess? M dx plus n dy, and now our dt is gone. Okay? And so we will start working on some problems with that tomorrow. Thank you. Boom!